This is DeformAr, a visual analytics framework for interpretable NER evaluation. As I mentioned in the paper and in the thesis, the purpose of this tool is to provide interpretable view of NER task, but not specifically NER. It can be designed or redesigned for other tasks as well. So it's a different way of interpreting and evaluating transformer algorithms in general, and BERT specifically. And the main focus, I was designed it for specifically for Arabic to provide interpretability and fine-grained analysis for Arabic, and used English as a baseline to compare it against. And as you see in the repo here, we have two phases: the extraction phase and the dashboard phase. In the extraction phase, we have a library that has various bits and pieces that we can apply throughout the extraction phase. We can start by generating the corpora itself. So here we have different files or different corpus from either file format in Arabic NER corpus, and Hugging Face for Cornell, for example. Using this corpora manager, we unify these into a unified structure, and then everything is integrated into Google Drive. However, this can be changed. So we use Colab and Google Drive for the cloud power or for the GPU power, and Google Drive because it's integrated and I can save things directly into Drive, even locally if I wanted to. So you can see that the experiment data, the corpora here, is generated automatically after we run this notebook, and then we can initialize the config files for Arabic NER corpus, and this specifies all the experiment setup and all the hyperparameters that we chose throughout the experiment. The results config file, so all these results config define the folder structure for the outputs that comes from the extraction phase. So the extraction phase is divided into fine-tuning. We fine-tune the model, then do a few extractions where we convert the hidden state into UMAP, for example, calculate some metrics, and then all of that gets populated in the folder structure. For example, for Arabic NER corpus, we have the configs saved automatically after this extractions, and then the extractions here is structured based on that config file that we've generated, and all that gets dynamically generated, and all the files with the naming convention, everything is defined from the outset when you set up the experiment. And as I said, the config file is saved, all the environment are also saved, the requirements for reproducibility, and the Python version as well, because it's quite important to know that, as Colab sometimes changes versions. So this is in the extraction phase. Everything is defined into pipelines. These pipelines define whether we want to do fine-tuning, extraction, and everything here can be run as a standalone. So we can do fine-tuning and then later we can do extraction, or we can run them together. So everything is decoupled basically. If we wanted to do any phase or redo any of the phases, we can do that. So the next phase is the dashboard phase, and this is based on Plotly Dash. And there are a few features here that has been introduced. As I said, based on the config files, we have a way of streamlining the saved data. So everything here is saved according to a structure, and based on a config file that we put here, we can decide how we read that data and which data we read, and everything here is managed by a config manager that go through the folder structure and the files and do all the transformation as needed. And that can be found here. It's called data manager. It's a data class with some functionalities and some transformations if needed, and then all that gets read through the data loader, and the data loader is the one that gives that output, says which data has been loaded, which bits has been failed to load or emptied, because these are the configs, I don't want to load them, so they are emptied out. And you can choose whether you read one variant or multiple variants. And then now we can move the cross-component analysis, and this cross-component analysis is dynamically generated through a config file. So inside that same config file, we decide the layout of the cross component tab, and then inside the tab we define the data component and all the analysis inside it, and the figures inside it, and that all gets populated in the cross component. And you can see that there's a different types of analysis and different figures under each type, and there are different components as well. So we have model components, we have evaluation. Through that config file we have that dynamically generated layout. So for the data component we have all the different analyses and the different figures, and if I click here it will generate, and if I click here it will generate a different layout and output and everything. And this structure allowed me to use a much simpler callback functionality. So now instead of having a callback for every figure, I have one or two centralized callbacks, one for loading the tab, and the other one is for dynamically updating the figures. So we have one figure canvas ID, and based on the component it decides whether we need to update the canvas here or the canvas here, and update it with what. So we can just dynamically have one component, one callback that dynamically update all the different canvases, which essentially one canvas with the same ID but attached to the component ID here. So that makes it really clean in terms of having one callback that connects everything else. And everything is mapped out through registry files. So we have a registry file here that define all the data managers or data helpers, and one for the model and one for the evaluation. So everything is nicely structured and cleaned. This is different from the behavior analysis tab, for example, which allows more elaborate functionalities. So for example, if we click here, this dynamically generate these outputs. If I click, it can change based on the selection, and we have a bidirectional selection. If I select here, it changes there, and if I select there, changes here, tells me where the representation is found. So these are dynamically updated together, and all these selection can be also reflected in here. So if I choose, for example, the predicted labels or the error type, it gives me the aggregate values for the selected elements based on that category, and then give me a summary statistics of all the numerical variables that we calculated. Same thing here for this analysis. We can view a breakdown of the agreements or whatever categorical values we have. And there are also static elements like the attention similarity. All these are static. They are not dynamically changed. They just exist once you go to the tab. Same thing for instant analysis. Everything is also aligned. If you select one sentence, it gets calculated. Everything here gets populated according to that. If we compute, we get all the similarity scores. The details of what these views means is within the thesis and within the paper, but I'm just going quickly through the different features that we can have. In terms of attention analysis, we have different views here, and I'm using BirdVis to help us look at attention analysis. So we have the metrics view, and we have the BirdVis view to help us understand the training impact, which also detailed in the thesis. So this is everything I wanted to talk about the tool. I hope you enjoy it, and thank you very much for listening, and sorry for the long video.